Okay, so today I'm going to talk about signal processing a little bit. And we're going to focus on signal processing for mass spectrometry, but you can apply, I mean, a lot of the techniques are quite general, so you could apply them to other uh, things where you need to, other data. So, for example, ChIP-seq would be a very typical example where you need to be able to find peaks in a noisy environment. And there are lots of other types of data that you can look at as a signal. So we looked at mass spec data and we saw that we get, even from a single Molotov spectrum, we get quite rich data. So we can zoom in and see the peptide isotope distributions. And then we also see that in some, where we have a strong signal, we have very little noise. But if we look at other uh, places, we have a lot of noise. And we have a combination of both electronic and chemical noise. And we, of course, have to deal with that in different ways. And then we have, if you look at LCM SMS data, then we also have the time dimension. Uh, and at each time we have a mass spectrum. And then also we take, continuously fragment peptides during the data acquisition. So we have another dimension, which is the fragment mass dimension. So these are the sort of data that we're going to think about. But first, before that, we're going to start looking at simpler signals. So here, the sort of prototypic signal would be a sine wave, which we get. One way of getting it is that we have a circle with a radius, and we rotate this radius, and the sinus of the angle is the A divided by C here. So that's how we can generate a sine wave. And the typical thing, if when the angle is 0, the value is 0 because A is 0. So we start out here at 0, and then it increases and goes periodically up and down. The few definitions we need to make. So one is the amplitude. So that's the deviation from 0. And the other one is the wavelength, is the distance between two minima, or the same as two maxima. So these are the. Then we have the other one, which is a cosine, which is now, sine was defined as A divided by C here, and cosine we defined as B divided by C. So we have, and so sine started at 0, cosine then is starting at 1, because at 0 angle B and C are equal. So it's just simply the same function, just slightly off. So then we can, of course, add together different kinds of sine waves. So here we have one sine wave, and then we add onto it another one which has a lower amplitude but a higher frequency. So then we get something that looks a little bit noisy, a sine wave that looks noisy. So now what we can do is we can actually, by adding different sine and cosine waves, we can actually construct any sort of waveform as we want. And then what we can do is apply what's called a Fourier Transform to these waves. And what that does is that it transforms a wave from the time dimension into a frequency dimension. So what we now have here is, and there are two parts to it. So what we don't need to actually go into these details, but what we do is, if we have the wave in the time dimension f of x here, then we multiply it by this function, which is an exponential, and it has here an imaginary, it's a complex function. So the transformation is actually in the frequency domain is a complex function, and the two parts to it means if we take the absolute value, then we get the amplitude. But why we need the both the real and the imaginary part of the function is because we also need to define what the phase is. So if we do this now for our function, this is the two sine waves that are added together, and we show here the absolute value. What we see is that there are two frequencies, and the amplitude of one of them is 5 times larger than the other. Exactly what we did to generate it. So this is just some code. You will get into that later, how to generate. So here we generate a vector that to define the x-axis here, and then we calculate the sine wave, and then this has one has amplitude 1 and frequency 1000, and the second one has amplitude 0.2 but 10 times higher frequency. So that's what we see here. Here we see that the peak at frequency 100 is 5 times higher than the one at frequency 1000. So now what we can do, we can also do the inverse Fourier transform. So now first we went from here, to frequency space, and then we can go back. And then we get exactly the same function. And there are as you see in Python, there's a simple function both for, so this is for the inverse and for the that we can use to do these transformations. So now what we can do is first we transform it to frequency space, and then we can, as we saw, if we take the whole frequency space and transform back, we get the function back. But if we cut in frequency space and only take, in this case, the low frequency, we get back the low frequency function. And if we take the high frequency, we get back the high frequency function. So this is a very useful tool, as you can now probably see, that to remove noise or to remove both, if we can, so what it's called, when we just select high frequencies, that's called the high pass filter. So we remove the low, slowly moving components, and we let the high frequencies through. And the same way that when we just let the low frequencies through, that's a low pass filter. And then we remove the higher frequencies. So now what we are interested in mass spectrometry is, of course, to characterize peaks. There are many ways we can characterize them. So one is we can look at where the maximum is, or we can see what's the height, what's the width of the peak, or what's the area, and also the centroid, so the sort of the weighted average of the peak. And then we can calculate things like mean, variance, skewness, and kurtosis of the peak. And
what was the x-axis there? Sorry.
So the x-axis is, in this case, it's undefined, but in mass spectrometry, it would be mass to charge. But in the general case, it can be also, so for ChIP-seq, it could be genomic coordinate, it could be all sorts of things. For example, if we look at an image and we cut a straight line through it, it could be distance. But for us, it's going to be mass divided by charge. So now if we define a peak f of x, so that, and we normalize it so that if we sum over f of x, we get 1. Then the mean is defined by multiplying x by f of x at each value and summing over that. And the variance is that we take this mean and the difference, take the squares of the differences from each values and weight that with f of x. So then, as you can see, we can continue this. So this is now to the first power, second power, and then it actually very nicely comes what skewness is when we do this to the power of 3, and kurtosis the power of 4. So skewness, you probably know, is that when we have one tail being much larger than the much longer than the other. And then kurtosis is defined so that if we define kurtosis like this, if we have a normal distribution, its kurtosis will be 0. And so what it says is that it can either that it's flatter or more peaked than a normal distribution. That's how when we talk about kurtosis. So now we can look at just the Gaussian to start with. A peak that's normally follows a normal distribution, and we can, this below here, sometimes I'm showing just code, so you can see how that it's quite easy to generate these distributions. And you'll know when Himanshu's back next week, he's going to go through more in detail how to use these and how more about the details. But you can even from these small snippets see that it's quite straightforward to do this. So here is the Gaussian, and then we take the Fourier transform of it. So what we see is that it's mainly composed of low frequencies, and it goes down to close to 0 amplitudes for higher frequencies. So as I said before, the skewness is 0 and the kurtosis is 0 for the Gaussian, and we can define what this is the full width at half maximum. Can be easily calculated from the standard deviation, and also the area is related to the height and the standard deviation in a straightforward way. So sometimes we get peaks that have much longer tails. So as you see here, this peak has a much longer tail than the Gaussian. And what we see here is that, remember, the Fourier transform of the Gaussian went down to 0 around 10, a frequency of 10, but this one continues up to higher frequencies, which then is what defines these tails. So this is a simple function also to define this, and it's called Lorentzian. And it's used to, especially in physics, to define certain peaks. It models certain peaks very well. So again, here we can calculate the full width at half maximum from this parameter gamma, and the area is also related to the height and the function gamma. Sometimes we want to model our data with a skewed peak. So this is one way of doing that. So you see that we have the the rise is much faster, and then we have a longer tail here. And you see again now to be able to describe these peaks in the frequency space, we need many more frequencies higher up. So then the other thing we need to look at is noise. So this is now normal noise that we've just generated from a normal distribution. And what we can do is, if we then make a histogram here, we see that the distribution of the noise looks normal. And another way to test whether it's how close to normal it is to do this probability plots that will show the data, and if it fits if it's close, the data is close to this straight line, we say that it's close to normal. So in this case, I mean, first of all, we knew that we generated the normal distribution, but this is just to show you one way of testing that. And if we convert this, do a Fourier transform, convert it to frequency space, we see that we have a lot of different frequencies, roughly represented at pretty close to equal amplitudes. So this is why usually normal noise is called white noise, because we have all the frequencies represented. So usually it's very much easier to work with data if we can transform the noise to normal. And sometimes this is easy, and sometimes it's not so easy to do. But it's always worth trying, because then we have much better tools to deal with it. So one case is when we have log normal noise. It's very simple. We just take the logarithm of the noise, and that's why most cases, like with microarrays and also in quantitative proteomics, most of the noise is distributed as a log normal, and that's why we use the log of the intensity as a measure. I mean, but it's not. You have to remember that it's not perfectly distributed as a log normal. So it's not one, and in different cases one could have more or less deviation. So it's always good to test it if one can. So as we see the log normal, it looks like there are a lot of peaks, but this is actually just a random distribution. And we see that it has a long tail, and also in the frequency space it doesn't just have the random distribution, but it has a peak at low frequencies. And we see that we have in a probability plot, we have a large deviation from a straight line. But again, in this case, we can very easily transform it to make it normal. So then we can have skewed noise. So now we're going to generate noise from a skewed distribution. And again, here you see that if we generate noise from this distribution here, it will also look quite different than our normal noise. It looks very much, there are more things that seem like peaks. But it's really just random. So again, if we generate the histogram, we see that we can recreate this similar distribution as what we use to generate the noise. And again, because it has this peak, we get the deviation in the probability plot from the straight line. And again, the same as for the then we had the log normal. Even in this case, this skewness will give rise to a peak at low frequencies. So now we can add these together. So we looked at peaks on their own, and we've looked at noise on its own. So now we're just going to take a Gaussian peak. We had in frequency space, remember we had this low frequency distribution that around frequency of 10 disappeared in this case. Then we have our normal noise, which had a lot of different frequencies contributing to it. And then if we add these two together, we get a noisy peak, which then has the pretty much adding up the two in frequency space also. So we get the characteristics of the Gaussian peak, and then adding on to it a lot of other frequencies. So now, as we did before, we can remove higher frequencies. So if we, for example, decide to cut all the frequencies that are, in this case, above 30, we will get so the black curve here shows what we get after that filtering, and the red is the original Gaussian, that without noise. So we see that we can get pretty good filtering just by simply cutting in frequency space and cutting pretty high up. So we still have some noise left, but it looks much better than our starting point. Then if we cut a little bit further down, now at 10, we see that we get a really nice smoothing. We have a little bit of noise out here, that but it looks really good. But then if we cut even further down, now we get a widening of the peak and ringing further away. So that's sort of so that's the trick, to choose where to set this limit, to cut away the noise but cut away as little of the signal as possible, so that we get, which this middle case is probably a very good compromise. So now there are other ways to do this also. So we're going to look at another way to do the filtering, and which is convolution. So this Wikipedia entry here describes it pretty well. So we have our function here. Let's say that we have function f, and then we want to convolute it with g, which is, so the f is rectangular shaped, and g is shaped as a triangle. So what convolution means is that we sum over, so we sweep one function over the other and sum all the products. So if we start here, so now also the other thing we do is we invert g. So now the triangle is in this direction. So when we move g in time, so before there is any overlap, it's 0. So that's out here. So then when they start meeting is at this point now. So now when we move a little bit further, we get an overlap like this, and that's this point here, and then we continue, and finally it's over and 0. So what we see is that by the convolution of these two becomes a function that first rises and then decays. So usually in our case, what the convolution that we're going to do is with a symmetrical function, and because we want to smooth, so these can either be, the simplest is a rectangle, we can use a triangle, or we can use a smoother shape, like in this case a Gaussian form. So as you can imagine, when we move these shapes over our function and then always calculate the overlap, what we're going to get is slightly wider features and a more smoothed function. So for example, here now we have the same as we looked at before, but now instead of cutting in Fourier space, we're going to move this over, which just means that we weight things differently. So here, if we vary the width of, so this is probably, here we chose a width that's not so, not wide enough. So we still have quite a lot of noise. And I don't know, sorry about the choice of colors here. There is almost no difference between the gray line and there's a little bit of difference here, out here. So that's why we still have a lot of noise left. But if you look in this case, the gray will start deviating quite a lot above 10. And then it's almost 0, but it's not completely 0. And then, but then again, if we choose the width too much, we get that the peak, our main peak widens. We do remove the noise very well, but our peak becomes too wide. So again, the choice in this case probably should be somewhere in between these two. So now if we look at a few examples now of peptides. So this is quite a small peptide. Here is the sequence. And we see that the isotope distribution, this is the ideal case. And then now, if we add both noise and make the peaks wider, we get, we see the first two peaks very well, but we almost don't see the third peak here. And then if we smooth it, we can see we can get a better definition of at least the first two peaks. But again, the third peak here, there is so much noise. We get the peak, but there is actually this other peak here is noise. So, but we can definitely lift out and see the peaks better. And this is another example of a larger peptide that has more isotopes. We see with wider peaks and noise. And here in this case, we can recreate the first few peaks quite well. So now we have another case where we have a lot of noise. One can't really see the peaks here in this case, but by smoothing we can get at least the two first peaks out. But as you see, the first peak is not centered at 0 anymore, and not the second one either. So we get, by when there's so much noise, we can recreate the peaks by smoothing still, but we get it's not a very good, the accuracy suffers a lot. And here is another case where we almost can't see the peaks from the noise, but then we can get quite nice peaks, but again we do shift the peak slightly, and we can't get, we don't get back the accuracy. So then there is another way which is called adaptive background correction, where we can do smoothing, and it's called unsharp masking in photography. So it's this, so we here now apply this convolution over it, and this is an example. So here we have the original image in the this half, and the unsharp masking applied to it. So what this does is that it enhances the features. So now what we can do is to combine this with the smoothing. Or not yet. So first we're going to apply just the adaptive background correction. So here we see our peak, but now what we have is we have very wide peaks. So the second and the third are just small humps on the first peak. By applying the adaptive background correction, that will enhance even the slightest small dip here, or even just if it's a shoulder. We can recreate the peaks, but again, we will shift them, so they won't be very, it's only the first one that will be quite accurately defined, but otherwise they're shifted. So then another example, we can, by applying this adaptive background correction, we can separate the peaks, but again, it's not perfect, because it's, as you see here, it's not centered around 0. So now if we have both noise and white peaks, then we need to combine smoothing with adaptive background correction. So here we see one example of where we have both noise and we have that the peaks are almost, the first two are almost indistinguishable, and I can't really see that where the third one is. But when we do this, apply adaptive background correction, we get the first 3 peaks. But then we also, these are all noise peaks here, so we do sort of create peaks out of the noise also. So that's the tricky part, that we, with all these filters that we apply, that one has to be careful how to use them. And again, one more example of both noise and then we can apply a filter. So so one more type of smoothing filter, which is very popular in, I think, in analytical chemistry in general, but also, especially in mass spectrometry, is Savitzky-Golay smoothing. So here we actually apply a polynomial of different orders to segments of the signal, and then, as you see, we can go, as we go up in polynomial order and in bin size, we can get very good smoothing. So if the bin size is small, we still keep some of the noise, and if we go up in bin size and keep the polynomial order low, then we get a widening of the peak. But if we do combine the two, we can get very nice smoothing. And this is the smoothing method that is, of course, requires more computation, because you need to fit a polynomial to each segment, but it will give you very good smoothing overall. Then we have cases like this, where we have a peak that sits on a slope. And then this is the same one, but with added noise. So what we see here is that so this is a Gaussian peak. So the gray here is the Gaussian without the slope. And then the magenta is the frequency distribution of the combined Gaussian with the slope. So here what we see is that it's not easy to separate the two. So that there's a big overlap in frequencies, and then this, when we add the noise, it's pretty much looks the same. just we have the noise background at high frequencies. So here we can't simply sort of apply a filter in frequency space, not a simple filter at least. But what we can do is, again, by using different smoothing, and over smooth this, we can find a way, something that will keep the peak but define the background. So in this case, maybe a bin size of 200 we can get sort of following the underneath the peak. And then if we subtract that, we get quite good retention of the peak, but we still keep we remove the slope. So this is something that we often have to do, that when signals are sort of different frequencies are overlaid. So sometimes we have, this is quite a common thing, that we have both noise that's very high frequency, and then we have low frequency components like this slope in this case. One thing that is often applied to a signal is the root mean square deviation. So we can use this. So we define a bin size, and then we calculate this function, which is just what's the deviation of this root mean square over the bin size. So an application of that would be, again, this background subtraction. So now we have different bin sizes, either 100 pixels, 200, or 300. And then we just calculate this root mean square deviation. And what happens is that over the background, even though it's on a slope, it will be pretty constant. There's some variation, but it's mainly due to the noise. And then when we have the peak, we get much larger. So now we have to choose the bin size again the right way, so that it's bigger than the peak. So probably this middle case would be the best, where we over the peak we get very large values. That's over some kind of threshold that we can set, and we can define this in different ways. So for example, here anything that's under this threshold is marked in red, and the peak is marked in black. So then if we select this threshold, we can then remove the background. So we talked about convolution. There are some other things that are related to it. One is cross-correlation and autocorrelation. So we talked about the convolution, that we used it to smooth. And actually, if we have a symmetrical function, it's that we do this with cross-correlation and convolution will give the same result. But the nice thing with the convolution, so it's the way people see it is that it describes the response of a linear time invariant system to an input signal. So that's one way of looking at it. And the other nice thing is that if we do a transformation into Fourier space, and then multiply every frequency, the intensity of every frequency, and then take the inverse Fourier transform, we get the convolution. So it's a easy way to calculate the convolution, is to go over to frequency space using a Fourier transform, multiplying the pseudo signals together, and then going back. So And cross-correlation, on the other hand, is to measure how similar two signals are. And the idea there is that you can, for example, use it if you have one signal and then another one is just shifted in time. If you take a cross-correlation, you can find that they are actually very similar, just shifted. And autocorrelation is when you do a cross-correlation with yourself, with the signal itself. And here you can find periodic signals. And in mass spectrometry, what we usually try to look for is adducts using this, using autocorrelation. So if you look at autocorrelation, so now here we have a signal, and then we have the same signal, and we're going to calculate the autocorrelation between them, and we see that if we do that, we get a large peak at around 0. And in this case, we actually don't have any adducts, so we don't get any other peaks. There are some noise peaks here, but pretty much autocorrelation is dominated always by the peak at 0. But now if we take a signal and we shifted it, so as you see here, this is everything is shifted by a constant compared to the signal up here. And then what we see is that it's shifted by 0.1. And then we see that in this case we get the peak at 0.1. So now if we have another case where we have the signal and then just randomly pick half of the peaks and shift them by 0.1 again, now we get the cross-correlation being that we have the peak at 0, because half of them are still at the same place, and half of them are shifted by 0.1, so we get roughly the same height in these. So then another way to compare two signals is to calculate the dot product. So here now we assume that the signals can be written as vectors. So if for a mass spectrum, we would take all the peaks in a spectrum, and each mass would be, where there's a peak, would be a dimension, and then the length of the vector in that dimension would be the height of the peak. So if we have identical vectors, then they would be, all the dimensions would be identical. So alpha would be 0, and then the dot product would be 1. So this would be the normalized dot product. And if we have perpendicular vectors, then the dot product is 0. And actually, so it's the dot product is related to the cross correlation, and it's the cross correlation at 0, at no shift. And this is something that we actually do use. We're going to come back to a little bit later when we talk about protein identification. And that we can use the dot product as at least part of the score of how similar two mass spectra are. So then we can look at what's the characteristic of dot product. So here we have different signal to noise ratios going from 0.1 to 10. And we have different number of dimensions. So if we first look at if we have 1,000 dimensions and we have a signal to noise ratio of 10, so this is the background peak. So this is just comparing two random vectors of dimension 1,000, and calculating their dot product. So we see that they're independent of each other, so it's random. So they're going to have a dot product of around 0. So then this might be difficult to see, but if we have the signal to noise ratio of 10 and just have identical vectors and adding a little bit of noise, the peak is very close to 1 here. You see the red peak here. And as we then increase the noise, so decrease the signal to noise ratio going over this way, we see that the peak at the random peak stays where it is, and the red peak goes down and gets closer to the random peak. And of course, when we decrease the signal even more, it will eventually overlap. So this behaves very well when we have 1,000 dimensions, and that's what we want, that it just gets, as the signal to noise ratio, it gets closer. But what happens in the case of when we have 10 peaks, then we have first of all a very wide distribution for the noise. And as we decrease the signal, we see that the red peak here gets really wide also, very fast, and it also slowly moves down. So there is the nice thing here, we had very little overlap between these two peaks, but in this case we do have an overlap. And that's why a lot of people have criticized to use the dot product as a score, because there is a big overlap between the signal and the noise. And the problem is that for most fragment mass spectra, we're going to be somewhere between 110 peaks, but probably closer to 10, more like 20, 30 peaks at most. So now autocorrelation, we're going to take the signal and we're going to shift the signal, and then we're going to add these two up, and then we're going to calculate the autocorrelation. And what we get then is since it's an autocorrelation function, we always get a large peak at 0. But in this case, we're going to get a peak both at minus 0.1 and plus 0.1. Because that's, remember, we did the shift here by 0.1 and added them together. So that's so by taking the autocorrelation here, we can deduce that there is a periodicity, even though it's difficult to see here. Maybe it's one can extract it this way. So another thing that we can do is to use coincidence to enhance the signal. So if we have an ideal signal here, so there is a peak at 0, and then if we add a lot of noise, you can see that there is some signal maybe at 0 and in these 4 measurements. But what we can do, if the noise is uncorrelated, we can, for example, one way to do the coincidence is to multiply these signals together. And if we do that, if we take the product of these 4 measurements, the signal that is very weak in each of these very nicely is lifted out of the noise.
How do you multiply?
You just multiply each point. Each point, yeah, pointwise. But it is I mean, it requires that the measurements are independent, and that you because if you have some correlation in the noise, it won't work. It's based on that the signal is correlated in the different measurements, but the noise is not. But you see the background here now looks very strange. It doesn't look. It's definitely not normally distributed like here. So you see, you have these big outliers. So that's something one has to definitely think about. And oh yeah, so this is the original noise, and then you see the noise of the product will have these very large tails, and also in the probability plot it has a large deviation from the normal from the line. So that's something that one has to worry about. So coincidence measurements do suppress noise, but one has to then deal with this, that it also transforms it from a normal distribution to a much something that's much more difficult to deal with. So another case is interference. So now again we have our ideal signal at 0, and then we have other signals. So in this case that are sometimes even larger than our regular signal, but these are again if they are uncorrelated, we can again do the just simply take the product, and because if they are spread out over the time, there won't be any irregularity to it. We can then apply this to clean up the signal. And this is something that people try to do quite a lot in different experimental setups. And especially in particle physics, this is what most measurements are based on, coincidences of several things. So for example, if a particle collides and falls apart into two particles, you measure both, and you have the coincidence that they have to come within a certain time frame and one of them to one detector over here, the other one to another detector here. So, but this it can be, now we looked at it as a way to process data, but you can also then, when you do the experiment, do it. And that's what also when you fragment peptides and you require that you see several of the fragments, maybe you do another fragmentation of the fragments, and these would all be coincidence measurements that use this kind of principle. Okay, so now we're probably ready to try to find peaks. So in general, what we say is that if we have a function and it's the derivative of the function is 0, then it's either a minimum or a maximum. And then, since we're interested in peaks, we're interested in maxima. We have that since derivative is first positive, then it's 0, and then it becomes negative as we go through the maximum. We need to the second derivative is of the function is negative at maxima, because we go from positive derivative to negative. But practically this method works very well for functions that are well defined, but since we have noise, it's not really, we can't really apply this in practice. We could try to smooth a lot but it's usually not used. So a more general way to go about this is to first characterize the signal and the noise, and then make a model of the data, and then decide on some kind of detection method, and then use, since we have a model, we can do simulations to then select the parameters that are to be used. So now this is just an example. We have noise. We have 3 peaks, one there and one here, and then one very weak one over here. So now we start with characterizing the noise, and the easiest way is, if we're lazy, is that we don't even try to remove the peaks. We just consider everything noise. So what we can do is we see that we can plot the histogram that looks pretty reasonable, but of course we have some outliers at this end, which are the peaks. And we see that when we do the probability plot, we get quite okay correspondence here, but we get, because we left the peaks in, we get a deviation here. So that might not be the best, but so we can use what we did before, the root mean square deviation, to remove outliers. So we calculate the root mean square deviation over this spectrum, and then what we get is the red here is the noise and the black the peak. So again, we didn't with this way detect this third peak here because it's very small. But now if we then do the same thing, we see that we get a nice Gaussian distribution, which we, again, so we started out with generating normal noise, and we now can fit a Gaussian and see that we actually get back, sorry, this is upside down, but the sigma is 0.2 and the x0 is close to 0, which was what we started with. So now we got the we characterized the noise, and we were lucky enough that it was normally distributed. And then we can look more closer at the peaks. They're a bit noisy, but we can since we don't know that much about them, it looks pretty reasonable to model them just by a simple Gaussian. So now we have our data, and then we can now we're just going to generate a peak here in the middle, and we're going to have different signal to noise ratios. And you see, when we have a signal to noise ratio of 1, we almost can't see our peak, but then as we increase the signal to noise, it gets clearer and clearer. So now, detection method, there are a few different ways to go about to detect signals. Probably the simplest one is just to select a peak width that we're looking for and then just calculate the moving average. That's probably, it's a robust way and very simple also. So what we do here now is we look at these simulations, and we start with try different signal to noise ratios, 1, 2, and 4 in this case, and then we choose a bin size for the moving average. And as you see in the when we have a high signal to noise ratio, we do pretty well with the small bin size. And then when we increase the bin size, we get a better signal to noise ratio, but the drawback is that the peak is less well defined. So that's always the question: what should one bin size should one choose in this case? And for when signal to noise ratio is lower, we need to choose a higher bin size to lift the signal out of the noise. And there are other methods. So, for example, the other way we calculate the root mean square deviation. We could apply that as a method. And in this case, it turns out that that doesn't work as well as the simple moving average. So now we have our peak, and we're going to just go back, and we looked at this before. So the kinds of things we want to find is where the maximum is, what the centroid area and height and full width at half maximum. Those are the things that we usually want to know. And we can then, as we calculate the centroid, which is simply the mean, the weighted mean, we can calculate the area and the height in quite simply. The problem is for these calculations is to actually define where the peak starts and ends. That's always the tricky part, because it's not very clear always. So for example, we have 4 examples here. Probably for this case we should probably start here and go over there, but then we have, this is a skewed peak and it probably starts here, but it's not completely clear where we should end. And this one is very difficult to say where, especially where it ends. So that introduces quite an uncertainty when there is noise present. So then we want to estimate the peptide quantity from a peak. And as we said, we always remove the background, and then we can do it in several different. One is peak height. And the advantage of peak height is very easy to calculate, but of course it's not usually as good because we don't use all the statistics that we have. We don't use the whole peak. So we can fit the curve to the peak. This is usually not done because we don't a priori know the peak shape, and it would take a very long time usually to do. Peak area is another way that the advantage is that here we use a lot of the statistics, but it has its drawbacks, and we'll get back to that later. So then what we have in the case of when we do LCMS is we have the time dimension also. And we can utilize that the always peaks appear, and the isotope distribution, it should appear at the similar times, then the peak grows and then it disappears. So this other dimension we can utilize and improve our peak detection, because we know that it should be quite continuous in time. So this is just another way to show the same information. So then the other thing we need to think about is sampling. So how many points do we need to measure over a curve and to get a good good quantitation? So what's your guess? How many points do we need to get, let's say, better than 90%? Any guesses? Estimate of the area. Yes, that's a pretty good. For example, even with 3 points, in this case, so the ideal value is 1, but 95% of the time we're going to get better than 0.87. So which is pretty good. And then if we then go up to 4 or 5 points, we will definitely 4 points we're better than 90%, and 5 points we're better than 95%. So it's I mean, most people are surprised how few points one needs, and you guys seem to have thought about this before, but most people guess at least 10 points, which is actually more than one usually needs. So let's go back to how one chooses. So if we how one chooses how to estimate quantity. So if we choose the peak height, The nice thing is that it's resistant to interference. So if you have a peak and then you have a shoulder from another peak, the peak height is quite resistant to that. But since we only use one measurement, there could be quite a variation because, as you see, some of the peaks have points that are uh, outliers. So then we have peak area, which is better statistics because we have more points that we average over, but it's much more sensitive to interference. And it's much more sensitive to how we choose where the peak begins and ends. And then again, curve fitting, which is would be good because we use the whole shape of the peak, but we do need to know the peak shape and it's slow. But so usually people choose between peak height and peak area. And for most practical purposes, it probably doesn't make a big difference because they have their drawbacks and advantages. So it's so the homework I'd like you to look at this time is how one can use background subtraction for smoothing. And there is a Perl script on the website that you can download, and we're going to go through more in detail what the different commands mean, but you can change the parameters so there it does two smoothings, and the idea is to remove, so we want to lift out these three peaks that are marked with the arrows, but this white peak in the middle is we want to remove as noise. So the way that you should choose the smoothing parameters is that you find the background that goes through under the three peaks with arrows, but then goes in and removes the peak in the middle. And then there is another smoothing parameter just to remove some of the noise also. So we want to find a background that's something like this red line, for example, that follows the white peak and the background but doesn't go into the small peaks. So for example, we would want something like this. So this would be the first, when we subtract this red line from the background, and then we smooth there's another smoothing that lifts out the three peaks. So that's play random, and you're already familiar with it from the previous class. Yeah. So this is the end of today's lecture, and so just quickly summarizing what I've talked about. So using Fourier Transform, we can transform between frequencies to frequency space and then back again. And we talked about how to detect and characterize signals. We talked about noise, how to characterize it, how to then build a model for both signal and noise, and then how to do some simple simulations to select thresholds and select parameters. Talked about filters, especially about smoothing filters, but also a little bit about adaptive background correction. We talked about detection methods that are based on either moving average or root mean square deviation. We talked about how we can to convolute signals, how to calculate the similarity between two signals with cross-correlation, and how to use autocorrelation to find periodic signals that are obscured by noise. How we can use the dot product to determine how similar two mass spectra are, and how we can use coincidence measurements or coincidence analysis of the data to enhance signal and suppress noise. And then finally, we talked a little bit about how to quantify peaks. And yeah, so that's the end of today's